At this very moment, 268 million kilometers above your head, an object that should not exist is defying every law we thought governed the cosmos. What we discover in the next 6 weeks could fundamentally rewrite humanity's understanding of our place in the universe, or confirm we've been watched from the stars all along. NASA's Neil Gehrels Swift Observatory detected water signatures on October 31, 2025, emanating in patterns that contradict every model of cometary physics we've developed in 4 centuries of astronomical observation. But here's what keeps astronomers silent. The leaked photographs show something that shouldn't be visible at this distance. So why can no one explain what we're actually seeing? Tonight we embark on a journey through one of the most extraordinary scientific mysteries unfolding in real time above us. An interstellar visitor designated 3I Atlas has entered our solar system carrying secrets that challenge the boundary between natural phenomena and something else. We'll examine documented scientific anomalies from credible observatories worldwide. We'll explore the leaked images causing quiet panic in astronomical communities. We'll investigate why institutional science has chosen complete silence over explanation. And we'll consider what this object might mean for our understanding of the universe and our place within it. This isn't ancient history buried in dusty archives. This isn't speculation about distant possibilities in some far future. This is happening now, observable through telescopes documented by independent sources, creating genuine confusion among credentialed scientists worldwide. The observation window closes in 6 weeks. After that, 3I Atlas disappears forever into interstellar space, taking its mysteries with it. We have one chance to understand what the universe has sent us. The universe has sent us a messenger. The question is, are we willing to read the message? In the vast cathedral of space, where distances are measured not in kilometers, but in the time it takes light itself to travel, visitors from beyond our solar system are extraordinarily rare. Our solar system extends roughly 100,000 astronomical units into the Oort cloud, that vast shell of icy bodies at the sun's gravitational frontier. Beyond that lies interstellar space, where even light takes years to cross between stars. The nearest star, Proxima Centauri, lies 424 light-years away, 40 trillion kilometers of emptiness. And yet occasionally, something crosses that gulf. These are interstellar objects, visitors from stellar systems beyond our own. They don't orbit our sun. They pass through following hyperbolic trajectories that carry them into our solar system from the cosmic dark and back out again into infinity. They are quite literally travelers from other worlds. The first confirmed interstellar visitor arrived in October 2017. Oumuamua Hawaiian for messenger from afar arriving first, moved too fast for solar gravity to hold. Its trajectory came from beyond our system. It was elongated, tumbling with a reddish surface and no obvious cometary tail. As it departed, it accelerated slightly in ways gravity alone couldn't explain. Scientists proposed explanations: outgassing, creating subtle thrust radiation pressure on an unusually flat object. Each was possible, none entirely satisfying. Oumuamua left in 2018, forever beyond further study. The second visitor, 2I Borisov, arrived in August 2019. Unlike its predecessor, it behaved like a standard comet, visible coma, developing tail familiar composition. Exotic in origin, conventional in nature. Discovered early 2025 by Atlas, the asteroid terrestrial impact last alert system 3I Atlas became the third confirmed interstellar object. The Hawaii and Chile telescope network flagged an object with hyperbolic trajectory, orbital eccentricity, exceeding 1.0 velocity beyond solar escape velocity, not bound by our star's gravity, passing through. The trajectory revealed something significant: relatively close approach to Earth. Perihelion in October 2025, closest Earth approach, December 19th at 0.4 astronomical units, roughly 60 million kilometers. Close enough for amateur telescopes to observe meaningfully. close enough for detailed spectroscopy, an opportunity to study material formed under alien stellar conditions. Imagine receiving a postcard from a place so distant that the light from there takes thousands of years to reach us. Three-Eye Atlas is that postcard written in the language of ice rock and time itself, but from the very first detailed observations, something was off. Not dramatically wrong, not obviously impossible, just inconsistent. Small discrepancies that didn't quite align with predictions. Observations that required explanations slightly more elaborate than they should have been. The kind of details that make scientists pause, recheck their calculations, and furrow their brows in careful consideration. It was as if the universe had sent us a postcard, yes, but written in a dialect we couldn't quite translate. The words looked familiar. The grammar seemed almost right, but something in the phrasing, some subtle choice of expression, hinted that this message came from somewhere more foreign than we'd expected. The anomalies began accumulating from those first months of observation. Each new data set added another question mark. Each attempt to explain one peculiarity seemed to reveal another. By autumn 2025, as Three-Eye Atlas approached perihelion and then swung past the sun toward its December encounter with Earth, the scientific community was quietly acknowledging that this object was not following the script, and that's when the photographs began to circulate. Long before telescopes transformed distant lights into worlds, before mathematics could calculate trajectories across the void, our ancestors watched the skies with a reverence born from existential necessity. The night sky was humanity's first clock-first, calendar-first map. The movement of stars marked seasons for planting and harvest. The phases of the moon governed tides and marked the passage of months. The sun's annual journey along the ecliptic told when winter would retreat and spring return. To ancient peoples, the sky was not merely beautiful, it was essential infrastructure for survival. But beyond the predictable movements of stars, moon, and sun, other phenomena appeared. Phenomena that violated the cosmic order. Phenomena that inspired awe and terror in equal measure. Comets. These hairy stars, as the Greeks called them, appeared without warning in the night sky. Unlike planets, which followed predictable paths along the zodiac, comets materialized from darkness, grew brighter, developed vast tails that stretched across the heavens, and then slowly faded back into invisibility. They were transient, unpredictable, and often spectacular. The Sumerians recorded observations on cuneiform tablets from 3000 BCE tracking Venus with precision modern astronomers still reference. They noted stars that burn in daytime and travelers against the wheel of heaven. We call them comets. The Babylonians developed sophisticated predictive models, understanding the Saros cycle, the 18-year eclipse pattern. They could predict lunar eclipses months in advance through mathematics born from centuries of careful observation. But comets defied prediction, appearing irregularly, making them omens, disruptions in celestial order that must signal divine messages. The Great Pyramid at Giza aligns to true north with 3-arc-minute accuracy. The 3 Giza pyramids mirror Orion's belt constellation associated with Osiris. The temple at Abu Simbel is oriented so twice yearly, sunlight penetrates to illuminate interior statues requiring precise solar position calculations. The Maya calculated the solar year at 365.2420 days, just 17 seconds from modern measurement, without telescopes. The Dresden Codex contains Venus tables predicting the planet's position across 584-day cycles with extraordinary precision. Halfway around the world, Polynesian navigators crossed vast Pacific distances using stellar navigation techniques of extraordinary sophistication. They memorized the rising and setting positions of hundreds of stars. They understood ocean swells and bird behaviors. They could dead reckon their position in the middle of the ocean without instruments, using only accumulated knowledge passed down through generations. These weren't primitive peoples stumbling through superstition. These were sophisticated observers developing empirical understanding through systematic observation across centuries. Even more remarkable are the oral traditions of indigenous Australians, which contain astronomical knowledge spanning more than 40,000 years. Aboriginal Australian traditions encode information about stellar positions, about changes in coastline from Ice Age sea levels, about animal species now extinct. This knowledge survived not through written records, but through songlines and oral transmission maintained with remarkable fidelity across 2,000 generations. When anthropologists began seriously studying these traditions in the 20th century, they discovered references to astronomical events that could be verified through modern calculation events that occurred tens of thousands of years ago, preserved in story and song. What all these cultures share is a profound attention to the sky, a recognition that celestial events matter, that the heavens speak to those willing to observe and remember. And when anomalies appeared, when comets blazed across the sky, when meteors fell to Earth, when eclipses darkened the sun, these events demanded explanation. The explanations varied by culture: divine messages, cosmic battles, harbingers of change. But the impulse was universal. Unusual celestial events have meaning. This is the tradition we inherit. When 3i Atlas appeared in our telescopes in early 2025, we were continuing a practice 10,000 years old. Different tools, charge-coupled devices instead of naked eyes, orbital mechanics instead of mythology, but the same fundamental activity, watching the sky for visitors, for anomalies, for phenomena that demand explanation. The same questions our ancestors asked still echo. What is this object? Where did it come from? What does its arrival mean? Our ancestors would have made offerings to their gods, perhaps, built temples oriented toward the position of this visitor, created myths to encode their observations for future generations. We create forum threads, process digital images, debate hypotheses in Discord channels. Different vocabulary, same wonder. When we observe 3i Atlas tonight in the pre-dawn hours, pointing our telescopes toward the constellation, Leo, we join an unbroken chain of human beings who have looked up and asked, what is that and why is it here? The ancient watchers knew something we sometimes forget in our technological sophistication. The sky still speaks. The universe still sends messages. And some of those messages arrive written in ice and rock, traveling from stellar systems so distant we will never see them, carrying information we have yet to learn how to read. Color in astronomy is not merely aesthetic. It is biography, the story of an object's composition, its temperature, its age, its history, written in wavelengths of light that travel across space to reach our instruments. When astronomers observe a distant object, they're not simply looking at it. They're dissecting the light it emits or reflects, breaking that light into its component wavelengths through spectroscopy. Different elements absorb and emit light at characteristic wavelengths. Iron has its fingerprint in the spectrum. So does carbon, oxygen, silicon, magnesium. By analyzing which wavelengths are present or absent, astronomers can determine what an object is made of without ever touching it, without ever traveling there. This technique has revealed the composition of stars hundreds of light years away. It's shown us that the universe is made of the same elements we find on Earth, hydrogen and helium dominating heavier elements, comprising smaller portions. It's confirmed that chemistry is universal. The periodic table works the same way in the Andromeda galaxy as it does in our laboratories. Color also reveals temperature. Hot objects emit blue-shifted light shorter wavelengths toward the blue end of the spectrum. Cool objects emit red-shifted light longer wavelengths toward the red end. By measuring color, astronomers measure temperature. A blue star is hotter than a red star. A comet's color tells us about surface composition and how that surface is being processed by solar radiation. This is established science. Reliable, predictable, foundational. So when 3i Atlas began changing color in ways that violated predictive models, astronomers noticed.
Initial observations showed neutral color, unremarkable gray-white. As it approached the sun, observers expected reddening. Comets contain organic compounds that under solar radiation break down into reddish-brown tholins through photochemical processes. This is well understood and predictable. 3I Atlas followed this script initially. By mid-2025, it shifted red exactly as predicted. Multiple observatories confirmed the change. Everything proceeded normally. Then the color changed again. Near perihelion, the object lost its reddish hue, shifting toward gray. Tholins don't disappear under continued radiation. They're stable processed end products. The reddening process is one way, yet the color changed. Scientists proposed explanations: rotation exposing different surfaces, red material sublimating to reveal gray underneath, fragmentation creating new surface. Each possible, each requiring unverifiable assumptions. Then came the third shift, a faint bluish tint in early November. Blue. Comets don't turn blue. Blue coloring in space is unusual. It typically indicates specific conditions, particular dust grain sizes that scatter blue light, preferentially certain ion emissions, or specific surface ices reflecting light in blue wavelengths. For 3I Atlas to develop a blue hue after perihelion passage, after already undergoing 2 previous color shifts, was anomalous. It suggested either compositional characteristics, unlike any known cometary body, or surface processes occurring that standard models didn't predict. Astronomers scrambled for explanations. Perhaps the blue came from carbon monoxide ice, which can appear bluish under certain conditions. Perhaps dust grains of a specific size were being ejected, scattering blue light through scattering the same phenomenon that makes Earth's sky blue. But carbon monoxide ice sublimates at relatively warm temperatures. By November 30th, the atlas was receding from the sun, cooling down. If CO ice were present and causing the blue color, it should have been more prominent when the object was warmer, not less. The timing was backward. And if dust grain scattering were responsible, the grain size distribution would need to be remarkably uniform, something that doesn't typically occur naturally in cometary dust clouds, where a wide range of particle sizes usually coexists. Once again, explanations could be constructed, but they required specific, unverified assumptions about the object's composition and behavior. The pattern was becoming troubling. Each new observation required new assumptions to explain. Imagine meeting someone whose eye color changed every time you saw them, not through contact lenses or tricks of lighting, but seemingly fundamentally. Their eyes are blue on Monday, green on Wednesday, brown on Friday. Each change has a potential explanation: medication, medical condition, lighting artifacts, your own misperception. But the accumulation of changes starts to strain coincidence. That's what was happening with 3I Atlas's color evolution. Each individual shift was potentially explicable through natural processes, but the sequence neutral to red, to gray, to blue over the course of 9 months didn't match any known cometary behavior pattern. The scientific literature on comets is extensive. Astronomers have studied thousands of comets from our solar system. They understand color evolution patterns. They've modeled surface processing under solar radiation. They can predict with reasonable accuracy how a comet's appearance should change as it approaches and recedes from the sun. 3I Atlas was an interstellar comet, yes, from a different stellar system potentially formed under different conditions. But the laws of chemistry and physics are universal. Carbon compounds should process the same way regardless of which star system they formed in. Ice should sublimate according to the same thermodynamic principles. Light should interact with matter through the same quantum mechanical rules. The color changes suggested something was different about 3I Atlas. Either its composition was more exotic than anticipated, or the processes affecting its surface were more complex than standard sublimation and irradiation could explain.
Some researchers quietly noted another possibility rarely articulated in official papers, but discussed in private conversations. What if the color changes weren't purely passive? What if they indicated active processes, not just material responding to solar radiation, but material being actively released or exposed through mechanisms beyond simple thermal sublimation? This was speculation carefully qualified, but it was speculation driven by observation. The data was clear. The interpretation remained murky. By the time the leaked photographs began circulating in early November, the astronomical community was already puzzled by 3I Atlas's behavior. The color changes had established a pattern. This object did not follow the script. It was unusual in documented, measurable, independently verified ways. The question was unusual within the range of natural cometary diversity, or unusual in ways that indicated something fundamentally different. That question remained unanswered, but it was being asked. Seriously, by credible scientists who understood cometary physics and recognized when their predictive models weren't quite working. The color of 3I Atlas was telling a story. We just weren't sure how to read it yet. In the cold mathematics of celestial mechanics, brightness follows predictable curves. An object's apparent brightness, how bright it appears from Earth, depends on straightforward factors: its size, its distance from the Sun, its distance from Earth, and its reflectivity. For comets, additional factors come into play. As a comet approaches the Sun, solar radiation heats its surface. Ices sublimate directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, the hazy atmosphere surrounding the nucleus and the tail. Both coma and tail reflect sunlight, significantly increasing the comet's overall brightness. This process is understood well enough to make predictions. Feed a comet's size composition estimate and orbit into computational models, and you can forecast its brightness curve, how bright it should appear at various points along its trajectory. The predictions won't be perfect. Comets are complex objects with variable activity, but they'll be reasonably accurate, usually within a magnitude or two. A magnitude in astronomical terminology is a measure of brightness, where each integer step represents a factor of about 2.5 in actual luminosity. A difference of 5 magnitudes equals a factor of 100 in brightness. The system is logarithmic and admittedly counterintuitive. Lower numbers mean brighter objects, and negative numbers indicate the very brightest. But the important point is, this brightness is measurable, predictable, and informative. Unexpected brightness changes indicate something happening that the models didn't anticipate. 3I Atlas exhibited unexpected brightness changes. Initial predictions based on the object's estimated size and cometary classification suggested it should brighten steadily as it approached perihelion, reaching a peak brightness in October 2025 when closest to the Sun, then gradually dimming as it receded. The brightness curve should have been smooth, following a predictable arc determined primarily by changing solar distance and consequent activity levels. That's not what observers saw. Through summer 2025, brightness fluctuated irregularly, sometimes brighter than predictions, sometimes dimmer. The variations showed periodicity, but didn't match standard rotation models. Astronomers proposed tumbling rotation, but brightness patterns didn't fit cleanly. Then came October 31, 2025, an unexpected brightening event when the object should have been dimming. Multiple observatories confirmed it: measurable sudden magnitude jump, then stabilization before resuming gradual dimming. Scientists describe this as confusing, meaning no comfortable explanation fits models within acceptable margins. Hypotheses emerged: fragment exposure rotation, changes volatile venting, each plausible, none entirely satisfying. Observation requiring explanation, explanation requiring unverified assumptions. But the October 31st event wasn't isolated. It was the most dramatic in a series of brightness anomalies that had puzzled observers for months. 3I Atlas was consistently behaving just outside the envelope of predicted behavior. Not wildly wrong, it was still recognizably comet-like, but consistently requiring amended explanations. Consider what this meant practically. Observatories allocate telescope time based on predicted phenomena. If a comet is expected to be at magnitude 10 on a given date, observers request equipment suitable for that brightness and schedule accordingly. When 3I Atlas kept deviating from predictions, observing programs had to adapt on the fly, requesting additional time-adjusting instrumentation, scrambling to capture data during unexpected brightenings. This wasn't merely academically interesting, it was operationally disruptive. And it suggested that something about 3I Atlas, its composition, its structure, its activity patterns, wasn't fitting the frameworks developed from decades of studying solar system comets. Some researchers began quietly discussing the possibility that interstellar comets might simply be more variable than their solar system counterparts. Perhaps formation in a different stellar environment produces objects with more extreme internal heterogeneity. Perhaps the journey through interstellar space, potentially lasting millions of years, exposing the object to cosmic ray bombardment and extreme cold, creates physical changes that make these visitors inherently unpredictable. This was reasonable speculation, but it was speculation driven by the need to explain observations that weren't matching predictions. It was theory catching up to reality rather than theory successfully predicting reality, always a sign that understanding remains incomplete. The brightness behavior of 3I Atlas, when combined with its color changes, painted a picture of an object more complex than initial categorization suggested. Not just a simple comet, an icy ball of primordial material following understood physical laws, but something with hidden variables, internal complexity or behavioral patterns that existing models couldn't fully capture. And this was the context into which additional anomalies emerged. Water signatures that didn't match expectations, coma development that fluctuated irregularly, and eventually images that claimed to show structure where only fuzz should be visible. The breathing object, as some observers privately began calling it, was demanding attention, demanding new observation, demanding explanations that existing frameworks struggled to provide. The universe was speaking. The language as yet remained partially opaque. Water is the signature of life as we know it, the universal solvent, the molecule that makes biology possible, the substance that covers 71% of Earth's surface. When we search for life elsewhere in the cosmos, we follow the water. Where liquid water can exist, life as we understand it becomes possible. When astronomers detect water around a comet, they're seeing the primordial stuff from which worlds form. Comets are icy remnants from the solar system's formation, preserved in deep freeze for 4.6 billion years. The water in comets is ancient, older than Earth's oceans, older than life itself. It carries isotopic signatures that reveal conditions in the early solar system, chemical fingerprints of the molecular cloud from which the sun and planets condensed. Detecting water in space isn't straightforward. Water molecules H2O don't emit visible light that our eyes or optical telescopes can see. Instead, astronomers look for hydroxyl radicals, OH molecules created when solar ultraviolet radiation breaks apart water molecules. These hydroxyl radicals emit characteristic wavelengths in the ultraviolet and radio spectrums, creating a detectable signature that indicates water's presence. The process is well characterized. When sunlight strikes a comet's icy surface, water molecules sublimate, transition directly from ice to vapor. The vapor forms part of the coma. Solar UV radiation then photodissociates some water molecules, breaking the HO bonds and creating hydroxyl radicals and hydrogen atoms. The hydroxyl radicals exist briefly before being further broken down or blown away by solar wind, but while they exist, they produce emission lines that telescopes can detect. By measuring the strength and distribution of hydroxyl emission, astronomers can estimate how much water a comet is releasing. By tracking how this emission changes as the comet moves closer to or farther from the sun, they can understand how the object's activity responds to solar heating. It's a powerful diagnostic tool. On November 2, 2025, Swift Observatory detected hydroxyl emissions from Three Eyes Atlas. Expected the object contained water ice being heated by the sun. What was unexpected was the pattern concentrated emission almost directional, as if water released from specific points rather than sublimating uniformly from sunlit surfaces. Comets can have jets from active regions, but Three Eye Atlas's pattern appeared more concentrated than typical jet behavior, less like passive sublimation, more like directed venting from discrete locations. The amount detected was also noteworthy, at the upper end of predictions, possibly exceeding them. Either the object contained more volatiles than estimated or release efficiency was higher than standard models predicted. Some researchers propose that the concentrated emission pattern resulted from Three Eye Atlas being a relatively small object where only one or two active regions dominated the outgassing. If most of the surface were covered in less volatile material or dust, and only specific areas were actively releasing water vapor, you'd see the concentrated emission pattern observed. This was possible, but it required assuming a specific surface configuration, heterogeneous composition with isolated active zones that couldn't be independently verified without detailed surface imaging, which was difficult given the object's distance and size. Others suggested that perhaps Three Eye Atlas was fragmenting, and what appeared as concentrated emission was actually water release from the exposed interiors of freshly broken fragments. Fragmentation would create new surface area of pristine ice which would outgas vigorously initially. Again, plausible. Again, lacking clear, confirmatory evidence. Observations looking for fragmentation debris gave ambiguous results. A few researchers privately noted another possibility rarely mentioned in formal settings.
What if the directional water release wasn't entirely passive? What if it indicated not just active regions, but genuinely active processes, perhaps internal heat sources, perhaps structural venting, perhaps mechanisms beyond simple solar-heated sublimation? This was highly speculative. Comets don't have internal heat sources. They're cold, inert bodies that respond passively to external heating from the sun. Suggesting anything more requires invoking processes that aren't part of standard cometary physics. But the hydroxyl data from Swift Observatory was unusual enough that even conservative researchers were beginning to wonder whether standard models fully applied to this object. Consider the broader pattern emerging by early November 2025. Unusual color, changes requiring creative explanation, brightness fluctuations not matching predictions. Now, water emission patterns appearing more concentrated and directional than typical cometary outgassing. Each anomaly could be explained individually through natural processes, but the accumulation was creating a picture of an object that persistently refused to behave quite as expected. This wasn't wild speculation or conspiracy theory. This was documented observation from credible instruments creating legitimate scientific puzzlement. Researchers were publishing papers noting these characteristics, presenting them at conferences, discussing them in technical forums. The mainstream scientific establishment wasn't denying any of this. They just weren't emphasizing it in public communications. The technical literature was filling with cautious phrases, requires further investigation, suggests unusual composition, merits additional observation. Each phrase was scientifically appropriate. Each phrase also acknowledged that the current understanding was incomplete. And then the photographs emerged. Early November 2025.
Images began appearing across astronomy forums, Discord servers, Reddit threads. Not from NASA or peer-reviewed journals, but from amateur astronomers who capture light each clear night. The images claimed to show three-eye atlas post-perihelion, visible again after weeks of solar glare. Some were conservative processing slightly enhanced, but recognizably fuzzy. Others, aggressive, bringing out faint details that raised questions, real features or processing artifacts. Consistent claims emerged. Structural visibility unusually distinct for the distance, geometric patterns suggesting angles and proportions, brightness consistency across multiple nights, uneven dust coverage revealing underlying structure. These claims were immediately contested. Processing experts suggested artifacts from aggressive enhancement. Others argued pareidolia pattern recognition in noise. Some attempted replication with varying results. The debate was technical detailed, sometimes heated. And notably, it wasn't happening between crackpots and serious observers. Professional astronomers were lurking in these forum threads. Amateur astronomers with decades of experience were participating. People with expertise in image processing were analyzing pixel data, calculating point spread functions, comparing enhancement techniques. This wasn't fringe conspiracy discussion. This was technical analysis by people who understood the tools and the challenges. And through it all, through weeks of online debate about these images, the institutions said nothing. NASA didn't issue a statement. No clarification about what their instruments had observed. No debunking of the circulating images. No educational post explaining how processing artifacts can create misleading appearance of structure. Nothing. The European Space Agency, which had tracked Three-Eye Atlas during its approach, remained silent. Major observatories that had observing time allocated for this object didn't publish image comparisons or offer expert analysis of the online claims. Silence. When obviously fake astronomical images circulate, and they do regularly, debunking is swift. Someone posts an image claiming to show an alien structure on the Moon or Mars. Within hours, experts identify it as a natural formation, a shadow artifact or outright fabrication. The debunking gets picked up by science communication accounts. The record gets corrected. Here, with images of Three-Eye Atlas that were generating substantial discussion in communities that include actual researchers, there was no such response. No confirmation, no denial, no clarification, just absence. That absence is itself fascinating.
It suggests one of several possibilities. Perhaps the images were deemed not worth institutional response, not credible enough to merit official comment. But that seems inconsistent with the detailed technical discussion happening among credentialed observers. If the images were obviously fake, or obviously artifacts saying so, definitively would be straightforward. Perhaps institutional sources hadn't yet analyzed the claims thoroughly enough to make definitive statements. Scientific caution is appropriate, but weeks were passing. Analysis doesn't require that much time when expertise is available. Perhaps, and this is more, speculative institutional sources themselves were uncertain. Perhaps they'd seen similar unusual characteristics in their own observations and weren't sure how to interpret them. Perhaps internal discussion was happening about whether and how to communicate findings that didn't fit comfortable frameworks. We cannot know which explanation is correct, but the pattern is clear. Unusual object behavior documented by official sources. Observation window opening that allows detailed imaging. Images circulating that claim to show unexpected features. Technical community debating those images with legitimate expertise. Official sources completely ignoring the discussion. It's the silence around the images as much as the images themselves that demands attention. Because while the authenticity and correct interpretation of these specific circulating images remains uncertain, the foundation remains. Three-Eye Atlas has exhibited documented anomalies in color evolution, brightness behavior, and water emission patterns. It has consistently required explanations more elaborate than standard cometary models predict. It is genuinely unusual in measurable, verified ways. The images circulating online aren't creating a mystery where none exists.
They're adding a layer to an existing one, a mystery that official observations established long before any photographs appeared in forum threads. Whether these specific images show what observers claim is one question. Why this object consistently behaves in ways requiring creative explanation is another. And why institutional response has been silence rather than clarification remains yet a third. All three questions remain unanswered. And the observation window, the brief time when new data can be collected that might resolve these questions, continues to close with each passing day. Science advances through parsimony, preferring explanations that require the fewest unsupported assumptions. When we encounter the unusual, our first obligation is to exhaust natural explanations before entertaining exotic ones. This principle, formalized as Occam's razor, isn't dogmatism. It's intellectual discipline earned through centuries of discovery, showing that most mysteries resolve through natural processes we already understand or slight extensions thereof. When we consider Three-Eye Atlas and its accumulated anomalies, the parsimonious explanation remains. All observations result from natural but unusual cometary behavior, not artificial. Not indicative of anything beyond known physics, simply an interstellar visitor whose composition and structure produce behavior at the edge of but still within the known range of cometary diversity. Let us examine how this explanation accounts for what we've observed. The color changes. Comets are complex objects with heterogeneous composition. Not every comet is identical. Formation in different regions of a stellar system, or in this case, a different stellar system, entirely produces different ice-to-rock ratios, different organic compound abundances, different mineral compositions. Three-Eye Atlas formed around a star that wasn't our sun. That star's luminosity, its spectrum, its radiation environment during planetary system formation, all potentially different from our sun's. The molecular cloud from which that stellar system condensed had its own unique chemical fingerprint, perhaps enriched in certain elements from previous supernova enrichment, perhaps depleted in others. An object formed under such conditions might have compositional layers unlike anything in our solar system, an icy mantle rich in certain organics that process into red coloration. Beneath that, a layer of different composition that appears gray when exposed. Perhaps pockets of carbon monoxide ice that, when they sublimate near perihelion, leave behind regions that scatter blue light preferentially. The sequential color changes we observed, neutral to red to gray to blue, could simply be different compositional layers being exposed as the object passes perihelion and outer layers sublimate away.
We're seeing a stratigraphic column of a small world's formation history revealed layer by layer as solar radiation strips it away. This explanation requires no new physics, just compositional heterogeneity, which we know exists in cometary bodies. The degree of heterogeneity might be unusual, but unusual isn't impossible. In a sample size of 3 interstellar objects, we hardly know what the normal range is. The brightness fluctuations. Rotation provides the key. Small bodies in space tumble. Their rotation states are complex, often involving precession and nutation wobbles and changes in spin axis orientation, especially if they're not perfect spheres, and especially if outgassing is asymmetric, creating tiny thrust forces that torque the rotation.
If Three-Eye Atlas is an irregularly shaped object, perhaps elongated, perhaps with one particularly reflective or active surface area, its tumbling rotation would create brightness variations as different aspects present themselves to the sun and to Earth-based observers. The irregularity in these brightness changes could result from the rotation itself being complex, not settling into a simple spin but wobbling chaotically. The October 31st brightening event. A fragment broke off, exposing fresh, icy interior that outgassed vigorously for a period, temporarily increasing observed brightness. Or perhaps a pocket of volatile material near the surface suddenly vented, creating a temporary outburst. Both phenomena are documented in solar system comets. 67 Pa Churyumov-Gerasimenko, observed close-up by ESA's Rosetta spacecraft, showed exactly such outbursts, sudden jets of material erupting from the surface when subsurface ice was suddenly exposed. The water emission pattern. Active regions explain this. Not every square meter of a comet's surface is equally active. Dust mantles can build up in some areas, insulating underlying ice. Other areas remain clear, allowing direct ice sublimation. The result is jets, collimated streams of gas and dust from specific active regions, while other areas remain relatively quiet. If 3I Atlas has particularly localized active regions, perhaps due to its composition, perhaps due to its rotation, keeping certain areas preferentially sun-facing, the concentrated hydroxyl emission pattern becomes explicable. It's not exotic behavior, it's just more pronounced jet activity than we typically see in well-studied comets, but within the range of natural cometary diversity. The enhanced images showing structure. This is where we must exercise particular caution, because here we're evaluating data of uncertain provenance through processing techniques that can create artifacts. But even granting the claims at face value that enhanced images show sharper features than expected, natural explanations exist. If 3I Atlas is fragmenting, we might be seeing multiple pieces, a partially disrupted object, held together loosely with visible gaps between fragments. From Earth's viewing angle, these gaps might create the appearance of edges or defined boundaries in enhanced images. Or perhaps we're seeing the nucleus itself more clearly than typical, because the coma is less dense than usual, fewer dust particles between us and the surface, allowing better visibility. If the object's activity is concentrated in jets rather than uniform sublimation, much of the surface might not be heavily obscured by dust, permitting enhanced images to resolve genuine surface features. Even geometric regularities can occur naturally. Crystalline structures in ice can create regular angles and patterns. Fractured rock breaks along stress lines that can produce relatively straight edges.
Natural processes, given the right conditions, can create striking patterns that suggest artificiality but are entirely geological. Consider the Giant's Causeway in Northern Ireland, hexagonal basalt columns formed by volcanic cooling that look almost architectural in their precision. Or the tessellated pavement formations in Tasmania, fractured rock slabs arranged in strikingly regular rectangular patterns through entirely natural freeze-thaw processes. Nature is capable of impressive geometry when the right physical processes are at work. Supporting this natural explanation, we have precedent, thousands of comets observed, many showing unusual characteristics. Comet Hale-Bopp exhibited unexpected brightness. Comet Holmes underwent an extraordinary brightening outburst in 2007, becoming 1,000,000 times brighter in just 42 hours, still not fully explained, but certainly natural. Comet Shoemaker-Levy 9 fragmented into 21 distinct pieces when tidal forces from Jupiter ripped it apart.
Comets surprise us regularly. They're complex objects. Our models are good, but imperfect. 3I Atlas might simply represent an extreme example of cometary diversity. Unusual, yes, but falling within the broad range of what's naturally possible. This explanation requires no violations of known physics, no invocation of unprecedented phenomena, no extraordinary claims requiring extraordinary evidence we don't have. Just acknowledgement that comets are diverse interstellar objects, might be even more diverse than solar system ones, and our models developed primarily from studying our local comets might not capture the full range of possibilities. The limitation of this explanation, it requires accepting significant coincidence. That one object happens to be unusual in its color evolution, and unusual in its brightness behavior, and unusual in its water emission patterns. And if we credit the enhanced images, unusual in showing visible structure through its coma. Each anomaly individually has a natural explanation, but the accumulation in a single object starts to strain probability. It's like meeting someone who is extraordinarily tall and ambidextrous and has heterochromia, different colored eyes. Each trait individually is naturally occurring, but finding all three in one person is statistically unlikely enough to be noteworthy. Still unlikely isn't impossible. The universe is vast. Space contains trillions of small, icy bodies. Statistical outliers exist. Perhaps we're simply observing one. This remains the most probable explanation not because it's certain, but because it requires the fewest assumptions beyond what we already know to be true about the universe. It is the baseline against which other hypotheses must be measured, the null hypothesis that alternatives must demonstrate superiority over. But probability isn't certainty.
And as we consider other possibilities, we must remain honest about both what this explanation handles well and where it begins to strain. The cosmos is not gentle. Stars explode, tearing themselves apart in detonations that briefly outshine entire galaxies. Planets collide in impacts that melt worlds and scatter debris across stellar systems. Gravitational titans tear smaller bodies to pieces. Stellar flares scour planetary surfaces. The universe is violent on scales that dwarf human experience. What if 3I Atlas is not a comet at all, but a tombstone, the fragment of a world that died violently in a stellar system we will never see? A piece of a planet, perhaps, or a large moon disrupted by catastrophe and flung into interstellar space, carrying with it the scars of its traumatic origin. This hypothesis that Atlas is a planetary fragment from a catastrophic disruption event explains several anomalies better than the standard cometary model while remaining entirely within known natural processes. Consider how it might have formed. Planetary collision scenario. 4.5 billion years ago in the early solar system, a Mars-sized object called Theia collided with the young Earth. The impact was catastrophic. Both bodies were partially vaporized. Debris from the collision coalesced in orbit around Earth, eventually forming our moon.
This isn't speculation. It's the most widely accepted explanation for the moon's origin, supported by isotopic analysis of lunar samples, showing compositional similarity to Earth's mantle. Such giant impacts were common in the late stages of planetary formation across the galaxy. As planets assembled from smaller planetesimals, the final stages involved massive collisions between near planetary-sized objects. Most such impacts result in one body absorbing or merging with the other. But sometimes conditions are right for massive disruption and ejection of fragments at high velocity. If 3I Atlas originated in such a collision in another stellar system millions of years ago, it would explain several characteristics. The heterogeneous composition, we'd be seeing material from different depths within a differentiated body, potentially including both surface material and interior layers with different mineral compositions. The structural characteristics hinted at in enhanced images, we'd be seeing geological layers, possibly even shock structures from the impact itself, fractured strata from a world that once had geology. The water signatures would make sense. Large planets and moons contain substantial water, often in subsurface layers or mixed with regolith. A fragment ejected from such a body could carry that water, which would sublimate when solar radiation heated it during passage through our inner solar system. Tidal disruption. Alternatively, 3I Atlas might have passed too close to a massive body, a gas giant, or even a star in its origin system. Every object has a Roche limit, the distance within which tidal forces from a massive body will overcome the object's self-gravity and tear it apart. For objects held together by gravity rather than material strength, this limit is typically about 2.5 times the massive body's radius. Comet Shoemaker-Levy 9 experienced this when it passed within Jupiter's Roche limit in July 1992. Tidal forces stretched and fragmented it into at least 21 distinct pieces that subsequently impacted Jupiter in 1994 in a spectacular display of cosmic violence. If 3I Atlas was partially disrupted by tidal forces before being ejected from its origin system, perhaps, during a close encounter with a gas giant that tore away outer layers but left the core relatively intact, we'd expect to see exposed interior material. The color changes could represent different compositional layers being exposed as outer material sublimates. The unusual activity patterns could result from the complex internal structure of a partially disrupted object. Supernova shockwave. Stars more massive than about 8 solar masses end their lives in supernova explosions. When a star's core collapses, it releases gravitational energy equivalent to the sun's total luminous output over its entire 10 billion year lifetime, released in just a few seconds. The resulting shockwave expands outward at thousands of kilometers per second, carrying mass equivalent to the sun's entire mass, traveling at appreciable fraction of light speed. If such a supernova occurred in a stellar system with planets, the shockwave would devastate those worlds. Atmospheres would be stripped away, surfaces would be scoured by radiation. The force of the shockwave itself could fragment smaller bodies or even partially disrupt larger ones. If a stellar companion to 3I Atlas's parent star went supernova in a binary or multiple star system, debris from shattered worlds could be ejected at high velocities. Some would fall back, some would enter orbits around the surviving star, but some could be accelerated to interstellar velocities, escaping the system entirely and wandering the galaxy as orphaned fragments of catastrophe. Such fragments would carry isotopic signatures of violent event elements created in supernova nucleosynthesis, potentially including radioactive isotopes, with known decay rates that could in principle be dated if we could analyze the object directly. They might show shock metamorphism changes in crystal structure from the extreme pressures of the shockwave. They would certainly be compositionally heterogeneous, containing both surface material and whatever deeper layers were exposed during disruption. Why this hypothesis matters? If 3I Atlas is a planetary fragment, it transforms the scientific significance of its passage. This would no longer be simply an interstellar comet, interesting, but essentially similar to our local comets, except for birthplace. This would be a sample of another stellar system's planetary formation processes. Potentially a piece of a world that once had surface geology, internal differentiation, possibly even geological activity. The geometric patterns some observers claim to see in enhanced images, they could be natural geological layering from a differentiated body. The crystalline structures of minerals formed under high pressure and temperature in a planetary interior, fracture patterns from the catastrophic event that destroyed the parent body. The directional water emissions, they could be coming from exposed interior layers where water was once chemically bound in minerals, serpentine clays, and is now being released as solar heating bakes those minerals. The structural visibility through the coma. If the object is primarily rocky with ice only in pockets or layers, much of the surface wouldn't be actively sublimating, creating less obscuring coma and allowing better visibility of underlying structure. Ancient parallel. The civilizations of Mesopotamia recorded falling stars, meteors, and understood them as objects descending from the heavens. They sometimes found meteorites, rocks that had survived atmospheric entry, and revered them as gifts from gods. The Kaaba in Mecca contains the black stone traditionally regarded as a meteorite, venerated since pre-Islamic times as a celestial object. These weren't superstitions. They were correct observations that objects from space sometimes reach Earth's surface. Modern science has confirmed this and extended the understanding. Meteorites are fragments of asteroids, pieces of worlds that never quite formed, or bodies that were shattered in ancient collisions. What the ancients revered as sacred stones we study as windows into planetary formation. The Allende meteorite, which fell in Mexico in 1969, contained
calcium aluminum-rich inclusions that were among the first solids to condense from the solar nebula, older than Earth, older than the Sun's fusion ignition primordial material from the solar system's birth. If 3I Atlas is a planetary fragment from another star system, it's an interstellar alendi, a piece of another world's history crossing the vast dark to reach us, offering glimpses of planetary processes beyond our solar system. Critical assessment. This hypothesis elegantly explains compositional heterogeneity, unusual structural characteristics, and the combination of comet-like ice with properties suggesting more coherent structure than typical comets. It requires no new physics, no unprecedented phenomena, just natural processes we know occur: planetary collisions, tidal disruptions, stellar violence.
The limitation is that we cannot confirm the origin story without detailed compositional analysis, isotopic ratios, crystallographic structures, mineral compositions that would require either much closer observation or sample return, neither of which is likely before the object departs forever. But as an explanation for why 3I Atlas behaves unusually while remaining entirely natural, the catastrophic fragment hypothesis is compelling. It fits the observations. It suggests testable predictions about what detailed analysis would reveal. It transforms the object from anomalous comet into something scientifically even more valuable: a messenger from a planetary catastrophe, carrying information about world building and world breaking beyond our solar system. There are questions that science whispers about late at night in locked offices after conferences end in private emails between trusted colleagues. Questions that risk reputations to ask publicly. Questions that institutional science treats with extreme caution, knowing that even posing them seriously invites misunderstanding and sensationalism. Tonight, in this contemplative space between certainty and mystery, we ask one of those questions. What follows is highly speculative. It represents one interpretation among many, carries significant uncertainty, and should not be presented as established fact. But scientific integrity requires examining hypotheses that fit observations, however uncomfortable those hypotheses might be. What if 3I Atlas contains non-natural components? Not claiming definitively that it's artificial, but asking whether the accumulated evidence warrants seriously considering that possibility alongside natural explanations. This requires careful framing. We're not suggesting space aliens or flying saucers.
We're asking whether an object exhibiting persistent anomalies, geometric features that multiple observers note, directional emission patterns, and behavior consistently requiring creative explanation, might include even partial, even ancient, even dormant evidence of technological processes. The intellectual foundation for asking. Harvard astrophysicist Avi Loeb has championed an approach to interstellar objects that prioritizes evidence over assumption. With Oumuamua, he carefully examined its acceleration anomaly, the unexplained change in velocity as it left our solar system, and noted that while natural explanations were possible, they required specific assumptions about the object's properties that couldn't be independently verified.
Loeb's position, often mischaracterized as claiming Oumuamua was alien technology, was actually more nuanced when conventional explanations require increasingly elaborate assumptions to fit observations. Scientific honesty demands considering less conventional possibilities, not embracing them, not promoting them, but not dismissing them reflexively either. His argument was methodological science advances by following evidence wherever it leads, not by starting from preferred conclusions and fitting evidence to match. Extraordinary claims do require extraordinary evidence. But evidence, when it exists, deserves examination, regardless of where that examination might lead. What would non-natural components explain?
Consider what we've observed about BI Atlas through this lens. The geometric patterns multiple observers claim to see in enhanced images, regular angular relationships, proportional dimensions, symmetries that seem statistically improbable for random fragmentation.
If these features are real, not artifacts, not pareidolia natural geology, can create some degree of regularity as we discussed. But there's a spectrum. At what point does regularity become so pronounced that geological explanations begin to strain? The directional water emissions detected by Swift Observatory concentrated almost jet-like, as if material were being expelled from specific points rather than sublimating uniformly from a sunlit surface. If this pattern is real and persistent, it resembles more closely what we'd expect from directed venting-controlled release than from passive ice sublimation. The brightness consistency, some observers note specific features maintaining similar relative brightness and position across multiple nights, suggesting either extremely stable structure or orientation control mechanisms beyond simple tumbling. The object's resistance to obvious fragmentation despite passing through perihelion, despite solar heating, that should stress a weakly bound rubble pile 3I Atlas appears to have remained relatively intact, if it's more structurally coherent than typical comets. Why? What provides that coherence? If these observations all have natural explanations, why do those explanations consistently require specific unverified assumptions? Why does this single object require so many amended models? One possible answer: because we're not looking at a purely natural object. Because some percentage of its structure, perhaps even a small percentage, involves engineered materials or systems that produce behaviors outside natural cometary ranges. Historical context. This isn't unprecedented speculation. In 1973, the British Interplanetary Society conducted Project Daedalus, a detailed engineering study of how humanity might build an interstellar probe using near-term technology. They designed a spacecraft that could reach nearby stars within a human lifetime using fusion propulsion. The design was practical enough that components could be engineered with 1970s-era technology. Currently, the Breakthrough Starshot initiative, backed by substantial funding and involving serious scientists, aims to send light sail probes to Alpha Centauri. The concept used ground-based lasers to push tiny spacecraft equipped with sails to 20% light speed, reaching the nearest star system in 20-25 years. If humanity in the early decades of spaceflight can conceive and design interstellar probe missions, why assume we're unique in doing so? In a galaxy 13.6 billion years old, containing hundreds of billions of stars, many with planetary systems, the question isn't whether technological civilizations exist elsewhere. Statistical arguments suggest they probably do, but whether any evidence of such civilizations has ever reached us. The von Neumann probe hypothesis. Mathematician John von Neumann proposed the concept of self-replicating machine systems that could reproduce themselves using raw materials they encounter. Applied to space exploration, a von Neumann probe would travel to another star system, use that system's resources to build copies of itself, then send those copies to other systems. Exponential expansion. Such probes wouldn't need to be operated by living crew or even be in active communication with their builders. They could be ancient autonomous following programming established millions of years ago by civilizations now extinct. They could explore the galaxy systematically over vast timescales, visiting stellar systems, collecting data, perhaps depositing monitoring equipment, then moving on. If 3I Atlas were such a probe, active, dormant, or partially functional, having traveled for eons through interstellar space, it would accumulate ice and dust during that journey. Cosmic sand blasting from interstellar medium particles might erode surfaces. It might appear comet-like externally, while containing internal structure that's decidedly not. Perihelion passage with its heating and increased solar radiation might activate dormant systems. Directional water emissions might be reaction control systems using available water as propellant. The geometric features visible in enhanced images might be genuine structure partially revealed as ice sublimates. This is speculation, highly speculative, but it's speculation that addresses accumulated observations in ways that don't require multiple, independent, unlikely natural phenomena all occurring in one object. Ancient wisdom meets modern speculation. Sumerian texts speak of Anunnaki beings from the heavens who brought knowledge. Egyptian mythology includes skyships and gods descending from Sirius. Vedic texts describe Vimanas, aerial vehicles of the gods. Native American traditions include star people arriving from the sky. These weren't observations of spacecraft, but they were attempts by pre-literate peoples to explain unusual phenomena in the sky using available conceptual frameworks. They saw something that demanded explanation. They explained it through mythology and deity. We have different conceptual frameworks now: physics, engineering, astronomy. When we see something demanding explanation, we explain it through technology and natural law. But are we so different from the ancients? Aren't we also creating narratives to explain observations that don't quite fit comfortable categories? Perhaps the ancients were right about this. The sky sometimes sends visitors. They interpreted those visitors through mythology. We would interpret them through science. Different languages for the same underlying observation. The universe is stranger than our models comfortably accommodate. Critical hedging.
This hypothesis must be stated clearly. Natural explanations remain most probable. The vast majority of unusual space objects are just that, unusual but natural. Nothing about 3I Atlas definitively requires non-natural explanation. Every anomaly could be natural if we allow for sufficient compositional and structural complexity. But could be, isn't, certainly is. And scientific integrity requires following evidence, not prior assumptions. If the geometric features multiple independent observers note are real, if the emission patterns are genuinely directional in ways difficult to explain through passive sublimation, if the object's behavior consistently requires explanations at the edge of natural possibility, then asking whether non-natural components might be involved isn't pseudoscience. It's cautious investigation of hypotheses that fit observations. The question isn't whether 3I Atlas is an alien probe.
The question is whether we're willing to examine evidence that might suggest that possibility, and whether institutional science's silence on these observations reflects caution or discomfort. Implications. If 3I Atlas contained even partially non-natural components, the implications would cascade through every human endeavor. Philosophy would be recontextualized. We're not alone, never have been. Theology would face profound questions about divine creation and humanity's special status. Sociology would scramble to understand how such knowledge affects human civilization. Science would be transformed. The methodological rules would remain observation hypothesis testing, but the questions asked would expand enormously. Astrobiology wouldn't be speculation about potential future discovery, but analysis of actual physical evidence. CT would shift from listening for signals to examining objects that might carry information physically. These implications are staggering enough that one can understand institutional reluctance to even discuss the possibility without overwhelming evidence. The social disruption could be significant, but avoiding discussion doesn't make uncomfortable evidence disappear. It just means the discussion happens in uncontrolled, often less rigorous forums. The core question: not, is 3I Atlas artificial, but does the evidence warrant seriously examining that possibility? And the honest answer given, accumulated anomalies that official observations confirm, might be yes. Even if the probability remains low, even if natural explanations are still preferred, The persistent pattern of observations requiring creative explanation suggests we shouldn't reflexively dismiss hypotheses simply because they're uncomfortable. Science isn't about comfort. It's about truth followed wherever evidence leads.
And the evidence surrounding Theta Atlas, while not conclusive, is certainly puzzling enough to merit serious investigation beyond institutional silence. Kepler gave us the laws of planetary motion elegant equations, describing how worlds sweep through elliptical paths around the sun. Newton gave us gravity's mathematics, the inverse square law that governs cosmic attraction across emptiness. Einstein gave us spacetime's curvature geometry itself, becoming dynamic under mass energy's influence. Each discovery brought order to apparent chaos, reducing the universe to equations that predicted and explained. But what happens when an object simply doesn't fit the equations? When observations persistently fall outside predicted ranges? When models developed from decades of data fail to accommodate a single visitor? The scientific method relies fundamentally on predictive models. Observe phenomena, develop hypotheses about underlying mechanisms, formalize those hypotheses as mathematical models. Test those models against new observations. When models successfully predict observations, confidence grows. When observations match predictions, understanding is validated. Theta Atlas has challenged multiple predictive frameworks. Not catastrophically, it hasn't violated conservation laws or broken fundamental physics, but persistently, measurably, across multiple independent observation types, it has produced data that falls just outside comfortable model predictions. Thermal models predict how temperature should vary with solar distance. They account for albedo surface reflectivity and thermal inertia, how quickly surfaces heat and cool. Feed in an object's size composition estimate, and orbital distance and thermal models predict temperature, which correlates with sublimation rates and consequent brightness.
For 3I Atlas, thermal models based on initial size and composition estimates predicted certain brightness levels at various points along its trajectory. The actual brightness measurements deviated from those predictions regularly enough that models required revision. Perhaps the albedo was different than assumed. Perhaps the thermal inertia was unusual. Perhaps the size estimate was wrong. Each revision was justified individually. But the accumulation of revisions, brightness model revised, then activity model revised, then composition estimates revised to match color. Observations creates a picture of models chasing data rather than successfully predicting it. Outgassing models predict how volatile materials sublimate under solar heating. They incorporate physics of phase transitions, thermodynamics of surface heating, and mechanics of gas escaping a body's weak gravity. These models have been refined over decades of cometary observation. They work quite well for solar system comets. For 3I Atlas, outgassing models struggled to match the directional hydroxyl emission pattern Swift Observatory detected. The concentration of water release seemed more focused than models predicted for an object of estimated size and activity level. Models could be adjusted. Perhaps active regions are more localized than typical. Perhaps rotation keeps specific areas sun-facing longer than average. But again, adjustments were being made to fit observations rather than observations confirming predictions. Color evolution models predict how surface processing under solar radiation should change spectral characteristics over time. These incorporate photochemistry understanding of organic compound behavior under UV radiation and experimental data from laboratory simulations. They've successfully predicted color changes in numerous comets. 3I Atlas's triple color shift, neutral to red to gray to blue, doesn't match any standard color evolution pathway models predict. Each individual color could be explained through specific compositional assumptions, but the sequence remains unusual enough that no single compositional model predicts all three transitions along the observed timeline. Rotational dynamics. Models predict brightness variations based on object shape spin rate and surface heterogeneity. An elongated object spinning rapidly creates predictable brightness oscillations as its cross-section visible from Earth changes. These models successfully determine rotation periods for countless asteroids and comet nuclei. For 3I Atlas, observers noted brightness variations that suggested rotation, but with irregularities that complicated clean period determination. Was it tumbling? Precessing did outgassing asymmetries torque its rotation, creating the irregular pattern. Each possibility exists within physics, but the data remained ambiguous enough that no single model fitted convincingly. This is the meta-pattern, not models being completely wrong, but models requiring continuous adjustment assumptions, requiring continuous revision explanations, requiring continuous elaboration. Each adjustment is scientifically legitimate, but the accumulation creates a picture of an object at the edge of predictive capability. Philosophical implication. What does it mean when reality consistently outpaces theory? Several possibilities exist, none mutually exclusive. First, perhaps our models are incomplete because our sample size is too small. We've studied thousands of comets, yes, but they're all from our solar system, formed under relatively similar conditions. 4.6 billion years ago from the same molecular cloud. We've studied exactly 3 confirmed interstellar objects. That's not enough data to know the full range of what's possible for objects from diverse stellar systems with different formation histories. If interstellar objects turn out to be more diverse than our local comets, and there's no reason they shouldn't be, then of course our models built primarily on solar system data won't perfectly predict their behavior. We're extrapolating beyond our training set, and extrapolation always carries uncertainty. Second, perhaps the universe contains more variety than our equations comfortably capture. Models are simplified representations of reality. They capture dominant effects while approximating or ignoring minor ones. For most objects, this works fine. The approximations are good enough, but occasionally an object comes along where the minor effects aren't minor, where the edge cases become central, where the simplifications break down. 3IR's Atlas might be such an edge case, not violating physics, but occupying a parameter space where multiple, usually minor effects become significant, simultaneously producing behavior that simplified models can't capture without adding complexity that the data doesn't yet justify. Third, perhaps we're measuring correctly but modeling wrongly. Perhaps some assumption embedded deep in cometary physics models an assumption so fundamental we don't even think to question. It doesn't apply to interstellar objects or to this particular object. Perhaps composition isn't homogeneous as typically assumed. Perhaps internal structure isn't rubble pile as many models assume. Perhaps activity isn't purely thermal-driven sublimation. Each, perhaps, is speculation, but collectively they point to a truth. Models are tools, not reality itself. When tools don't quite work, sometimes the tool needs refinement. And sometimes the object you're trying to understand is more complex than the tool was designed for. Ancient parallel. The Maya developed calendars of stunning precision without telescopes, without electronic calculators, without even a place value number system that included 0, though they invented that too independently from old world mathematicians. They achieved their precision through observation, centuries of careful recording, pattern recognition, mathematical relationships, extracted from data rather than derived from theory. When European astronomers with their heliocentric models and Newtonian mechanics encountered Mayan astronomical tables, they discovered something humbling. The Maya had been more accurate about Venus's cycles than European models predicted. The Maya didn't have the correct theory of orbital mechanics. They didn't need it. They had the observations, the patterns, the empirical relationships that worked, regardless of underlying mechanism. Perhaps modern astronomy faces a similar moment with 3I Atlas. We have sophisticated theories, powerful models, centuries of theoretical development. but we have one object that doesn't quite fit those theories. Do we adjust observations to match theory, or do we acknowledge that theory, however sophisticated, remains an approximation of reality and must bend when reality insists? The Maya would have simply observed, recorded, noted the anomaly, and looked for patterns in the anomaly itself. They wouldn't have needed to explain why. They would have known what. Modern science demands both what is happening and why. But when why remains elusive, what still matters. And what 3i Atlas is doing is measurably unusual regardless of whether our current frameworks can comfortably explain it. The meta question persists. What does it mean when an object's behavior consistently requires creative explanation? When each observation adds another note saying, unusual requires further investigation. When institutional response is not confident prediction, but cautious silence, perhaps it means our understanding of interstellar objects is still forming, still incomplete, still requiring more data before confident claims can be made. Science often proceeds through such periods of uncertainty before clarity emerges. Or perhaps it means this specific object is genuinely anomalous in ways that transcend typical natural variation. Not impossible, not violating physics, but rare enough complex, enough unusual enough that it demands attention and investigation beyond routine survey work. The mathematics aren't refusing to align out of stubbornness. They're revealing gaps in our understanding, highlighting assumptions that might not hold, pointing toward complexity we haven't yet fully characterized. The universe is teaching. The question is whether we're listening. In the age of instant communication, when astronomical discoveries are live tweeted by observatories, when press releases are drafted for minor findings, when citizen science projects invite public participation in data analysis, the silence surrounding 3i Atlas's anomalies is itself anomalous. Consider the typical pattern of astronomical communication in 2025. When New Horizons flew past, Pluto images were released within hours. Press conferences held, scientists gave interviews explaining discoveries in accessible language. When the Event Horizon Telescope captured the first image of a black hole's event horizon, the achievement was announced simultaneously at press conferences on multiple continents. The scientists became temporarily famous. The image flooded media worldwide. When interesting, transient events occur, supernovae, gravitational wave detections, asteroid close approaches, amateur astronomers often learn about them in real time through automated alert systems. The astronomy community has embraced transparency and public engagement as core values. Against this backdrop of open communication, the institutional silence around 3i Atlas's unusual characteristics stands out starkly. The pattern of non-response. When the enhanced images began circulating online in early November 2025, showing alleged structural features, the immediate expectation was institutional response. Either confirmation, yes, we've observed similar features, here's what we know, or debunking, those images show processing artifacts, here's why, or educational clarification, here's how image processing can create misleading appearance of structure. None came. NASA, which operates the Swift observatory that detected the unusual hydroxyl emission pattern, issued no statement, no press release explaining the water signature observation, no educational outreach about what hydroxyl emissions mean or how they're measured, just silence. The European Space Agency, which tracked 3i Atlas during its approach to Mars and had unique viewing angles from Mars orbiters, published no comparative analysis of their observations versus the circulating amateur images. No expert commentary on whether the alleged features were consistent with their data. Silent. Major ground-based observatories. Gemini Keck, the very large telescope Subaru that have capable instruments and observing time allocated for solar system objects, issued no comparative imaging, no high-resolution photographs from professional equipment to either validate or contradict the enhanced amateur images. Nothing. The Planetary Society, An organization dedicated to public engagement with space science didn't commission explanatory articles. Sky and Telescope magazine didn't publish detailed analysis. Popular astronomy websites didn't interview experts about the claims circulating online. The silence was comprehensive. Historical patterns of response. This silence is particularly notable when contrasted with how institutions respond to other claims about astronomical objects. When images circulate claiming artificial structures on Mars faces pyramids, alphabet letters, debunking is swift. NASA's Mars missions have photographed the same regions at higher resolution, showing clearly that the Quaquinal structures are natural geological formations combined with lighting angles and pareidolia. The agency doesn't ignore these claims, it educates about them. When claims emerge about alien megastructures around Tabby's star after unusual dimming was observed, professional astronomers engaged publicly with the hypothesis. They explained why, while extraordinarily unlikely the idea wasn't impossible, then worked to determine the actual cause, which turned out to be natural, possibly involving dust clouds. But the engagement happened. Papers were published. Observations were conducted. Communication was maintained. When the WOW signal, a strong narrowband radio signal detected in 1977 that looked potentially artificial, became public knowledge, astronomers didn't remain silent. They discussed it, attempted to reobserve the location, published analyses. Decades later, when a natural explanation involving cometary hydrogen clouds was proposed, that research was also published and discussed. The pattern. When claims of unusual phenomena circulate, scientific institutions engage. They investigate, they clarify, they educate. What they don't typically do is ignore completely. Yet with 3i Atlas, despite images generating substantial technical discussion in communities that include professional researchers, despite documented observational anomalies in official data, despite an ongoing observation window that allows verification or refutation silence. Possible explanations for institutional silence. Several explanations exist, ranging from benign to concerning. Responsible caution. Perhaps institutions don't want to sensationalize incomplete data. 3i Atlas is being studied. Analysis is ongoing until peer-reviewed papers are published with careful conclusions. Making public statements would be premature. This is scientifically responsible. Avoid overstating significance of preliminary data that might not hold up under further scrutiny. This explanation makes sense for ongoing research not yet ready for publication, but it doesn't explain why institutions haven't addressed the circulating enhanced images, clarifying that those images aren't verified by institutional observations, explaining how processing can create artifacts, offering expert context. None of this requires complete research. It's just basic science communication. Institutional conservatism. Academic and government scientific institutions are risk-averse. Careers depend on maintaining credibility. Making claims that turn out to be wrong damages reputations. With something as potentially controversial as unusual interstellar objects showing unexplained characteristics, erring on the side of silence might seem safer than engagement. If there's any possibility that the anomalies might suggest non-natural components, even if that possibility is remote, institutions might choose to say nothing rather than risk being associated with claims that could be ridiculed. The cultural stigma against discussing potential techno-signatures is substantial. Better silent than sorry. This explanation fits human institutional behavior, but it reflects poorly on scientific courage. If evidence exists that warrants investigation, institutional authority should be used to facilitate that investigation, not to avoid it out of reputational concern. Resource allocation. Major observatories have planned observation schedules years in advance. Telescope time is allocated through competitive proposal processes, diverting resources to investigate claims from online forums even when those claims have some technical merit disrupts planned research programs. Additionally, the expertise required to properly analyze the claims spans multiple specialties: cometary physics, image processing, spectroscopy, orbital mechanics. Assembling teams with appropriate expertise, conducting new observations, performing careful analysis, all of this takes time and resources that might not be readily available. This is practically understandable, but it suggests institutional priorities might not align with scientific opportunity. 3I Atlas is a rare visitor observable for limited time. If it's genuinely unusual and official data suggests shouldn't institutional resources be deployed to maximize understanding during the brief observation window, genuine uncertainty. Perhaps the most concerning possibility: institutions aren't sure how to communicate what they're observing. Perhaps internal analysis is happening, but it's generating debate rather than consensus. Perhaps different experts are interpreting data differently. Perhaps some researchers see anomalies that others think are over-interpretation. In such situations, issuing public statements becomes difficult.
What do you say when your own experts disagree? How do you communicate uncertainty without either sensationalizing or seeming dismissive? If institutional observations show unusual characteristics that don't have comfortable natural explanations, but also don't definitively prove anything exotic, the safest bureaucratic response might be say nothing until consensus emerges. This explanation, while speculative, fits the pattern. It explains why neither confirmation nor debunking has emerged, because neither is yet justified by consensus understanding. It explains why enhanced amateur images are ignored rather than addressed, because institutional images might show similar features that haven't been conclusively interpreted. It suggests that the silence isn't suppression, but uncertainty, the kind of genuine scientific uncertainty that exists when observations don't fit comfortably into existing frameworks, and the community hasn't yet agreed on what those observations mean. Historical precedent. In 1967, radio astronomers Jocelyn Bell and Anthony Hewish detected remarkably regular radio pulses from space, pulsing every 1.33 seconds with such precision it seemed artificial. They jokingly labeled the source LGM-1, Little Green Men. They didn't immediately announce potential alien signals. They continued observing. They checked for instrumental errors. They discovered 3 more such sources in different parts of the sky. Only after establishing that the phenomenon was natural neutron stars spinning rapidly and beaming radio waves like lighthouses did they publish. Their caution was appropriate. Had they announced possible alien signals without thorough investigation, and had those signals turned out, natural credibility would have been damaged. By waiting until understanding was solid, they could publish confidently, explaining both the phenomenon and its natural cause. Perhaps something similar is happening with 3I Atlas. Perhaps institutional observations show unusual characteristics that require time to understand. Perhaps the silence reflects not suppression, but appropriate scientific caution, investigating before announcing, seeking consensus before communicating. But there's a crucial difference. Bell and Hewish discovered pulsars in 1967. They published in 1968, 1 year later. 3I Atlas was discovered in early 2025. We're now in November 2025, nearly a year, and the observation window is closing. By December, the object will be too distant for detailed study. Whatever institutional observations exist, whatever analysis is ongoing, time is running out to conduct additional observations that might resolve ambiguities. The pulsar discovery could be investigated at leisure. Pulsars don't leave, but 3I Atlas is leaving. If institutional understanding is incomplete, if uncertainty persists, if debate continues about interpretation, the opportunity to gather clarifying data is vanishing. That's what makes the silence particularly puzzling. If institutions are uncertain, shouldn't they be loudly calling for more observations, more telescope time, more resources dedicated to understanding this visitor before it departs forever? Instead, quiet.
Ancient parallel. The burning of the Library of Alexandria destroyed countless texts, knowledge accumulated over centuries lost in flames. We don't know exactly what knowledge disappeared. That's the tragedy of lost information. But we know the loss set back human understanding in multiple fields, requiring centuries to rediscover what had been known and forgotten. Modern institutional silence isn't burning books, but it's a different kind of information loss. If understanding exists about 3i Atlas that isn't being shared, if observations show unusual characteristics that aren't being discussed, if the closing observation window passes without maximizing data collection because institutional resources aren't being deployed, future generations might look back at this moment as an opportunity missed knowledge that could have been gained but wasn't because communication failed. The core question: who decides what the public learns about the universe? When scientific institutions choose silence over communication, whether from caution, uncertainty, resource constraints, or concern about credibility, they preserve institutional authority, but sacrifice collective investigation. In an era of distributed observation capability, when amateur astronomers have professional-grade equipment, when image processing software is freely available, when online communities can analyze data, collectively, can gatekeeping even work anymore? Perhaps the silence reflects institutional discomfort with this new reality. Perhaps it represents recognition that once observations are made, public interpretation can't be controlled. Perhaps it's simply bureaucratic inertia, the machinery of large institutions moving slowly while opportunities move quickly. Whatever the cause, the effect is clear. An interstellar visitor exhibiting documented unusual characteristics is being discussed more thoroughly in online forums than in official communications. And that pattern, technical detailed discussion happening in unofficial spaces, while official sources remain silent, is itself revealing. The Library of Alexandria burned through negligence and conflict. The library of knowledge about 3i Atlas might be incomplete through caution and silence. Both represent losses to human understanding. The observation window is open now. It closes soon. The silence continues. Time in astronomy usually operates on scales that dwarf human experience. Stars live billions of years. Galaxies evolve over cosmic epochs. Light from distant objects takes so long to reach us that we see the universe's past, not its present. The farther we look, the further back in time we observe. But occasionally, briefly, the universe operates on human timescales. Sometimes events unfold over days, weeks, months. Sometimes opportunities arise that must be seized immediately or lost forever. And sometimes the cosmos doesn't wait for bureaucratic processes or consensus building or institutional schedules. Right now, this week, these 6 weeks, that's the window we have to observe and understand 3i Atlas before it departs our solar system forever.
The specific timeline is unforgiving. November 11th, 2025. 3i Atlas reappears in pre-dawn skies. For several weeks prior, it was too close to the sun's position in the sky for practical observation. Trying to observe, it would be like trying to see a candle flame next to a spotlight. But on November 11th, it emerges from solar glare, visible again in the eastern sky before dawn in constellation Leo. This is when amateur astronomers with appropriate equipment can begin systematic observation. When independent data collection becomes possible. When the distributed network of observers worldwide can point their telescopes at the same target and begin accumulating images, measurements, independent verification. December 19th, 2025, closest approach to Earth. At that point, 3i Atlas will be 0.4 astronomical units away, about 60 million kilometers. Not dramatically close, but close enough that telescopes with 8-inch apertures or larger can resolve it as more than a point source.
Close enough that spectroscopic analysis becomes more feasible. Close enough that if structural features exist, they have the best chance of being resolved. This is the optimal observation date, the closest three-eye atlas will ever be to Earth in all of human history. After December 19th, it begins receding, not returning. Its hyperbolic orbit ensures it's leaving the solar system permanently. Late December 2025. Practical observation window closes. By year's end, the object will be far enough away that observing it requires large professional telescopes with significant time allocations. Amateur observation becomes impractical. Even professional observation becomes challenging as the object dims and its angular size decreases. After early January 2026, Three-Eye Atlas effectively becomes unobservable without major dedicated telescope campaigns that would need to be proposed, reviewed, and scheduled far in advance. By then, the object will be a fading dot impossible to characterize in detail, carrying its mysteries away into interstellar space. 6 weeks. November 11th to December 1st. That's the window. That's all the time we have when Three-Eye Atlas is close enough, bright enough, positioned correctly for detailed observation that might resolve the questions its behavior has raised. What's possible in 6 weeks with appropriate equipment and clear skies? Quite a lot. Amateur astronomers with 8-inch to 16-inch telescopes equipment, costing anywhere from $2,000 to $20,000, well, within reach of serious hobbyists, can capture meaningful images. Not Hubble quality, but sufficient to show the object's appearance, any visible coma, development brightness variations over multiple nights. Processing those images through stacking and enhancement techniques can bring out details invisible in single frames. With enough exposures captured over multiple nights, rotation periods can be determined. Color information can be measured through filters. Changes in appearance can be documented. If hundreds of observers worldwide participate, each capturing images from their location, the combined data set becomes substantial. Different viewing angles, different atmospheric conditions, different equipment, all provide independent confirmation or refutation of claimed features. Consistency across independent observations builds confidence. Discrepancies reveal artifacts or processing errors. This is the power of distributed observation. No single authority controls the narrative when dozens or hundreds of independent sources collect data simultaneously. If structural features are real and persistent, multiple observers should see them. If they are artifacts or processing errors, they should appear randomly without consistency across different equipment and techniques. Spectroscopic analysis becomes possible at closest approach. While full spectroscopy requires larger apertures, some amateur setups can conduct basic spectral analysis using diffraction gratings. Professional observatories with allocated time can conduct detailed spectroscopy. Composition can be determined. The hydroxyl emission pattern can be characterized more precisely. Temperature can be measured. If the unusual water emission pattern Swift Observatory detected is real and persistent, other instruments should confirm it. If it was anomaly or misinterpretation, that should become clear with additional data. 6 weeks is enough time for multiple independent spectroscopic observations by different instruments. The opportunity for verification or refutation. The circulating enhanced images showing alleged structural features, are they real or artifacts? 6 weeks allows testing. If those features are genuine characteristics of Three-Eye Atlas, other observers using comparable equipment and processing should reproduce them. If they're artifacts specific to certain processing techniques or misinterpretations of noise, they shouldn't reproduce consistently. This is how science resolves ambiguity through replication. Independent observations either confirm or contradict initial findings. With Three-Eye Atlas visible and accessible to amateur observation, the capability for such replication exists now for 6 weeks, then vanishes. What's at stake if these 6 weeks pass without systematic observation, without coordinated data collection, without serious effort to answer the questions? 3i Atlas's behavior has raised, we lose the opportunity permanently. After 3i Atlas departs, all we'll have is whatever data was collected during its passage. If that data is insufficient to resolve disputes, if key observations weren't conducted, if the observation window was squandered through institutional inaction and lack of public participation, future researchers will look back and wonder why we didn't do more when we had the chance. Consider how we regard the Tunguska event of 1908, a massive explosion in Siberia that flattened 2,000 square kilometers of forest. By the time researchers reached the site decades later, much evidence had degraded or disappeared. We still debate what caused it comet-asteroid. The remote location and delay in investigation means we'll probably never know definitively. Or consider Oumuamua. By the time we realized how unusual it was already leaving the solar system. Proposed missions to intercept it would take decades to develop and launch. We'll never get close-up observations. All we have are the limited measurements captured during its brief passage, forever insufficient to resolve debate about its nature. 3i Atlas offers a different situation. It's still here. It's observable now. For 6 weeks we can gather data. The question is, will we ancient parallel? Polynesian navigators undertook voyages across Pacific distances using seasonal winds and ocean currents. These journeys required precise timing, launched too early or too late, and conditions would be wrong. Winds wrong, currents wrong, stellar positions for navigation. The window for each voyage might last only weeks. They understood something modern civilization sometimes forgets. Some opportunities don't wait. When conditions align, you must act or the opportunity passes and might not return in a lifetime. The universe has aligned conditions for observing 3i Atlas. The object is close. The observation window is open. Amateur equipment is sufficient for meaningful data collection.
Processing techniques are well developed. Online communities exist for data sharing and collaborative analysis, everything necessary for answering the questions 3i's Atlas raises exists right now. Accept action. Accept participation. Accept recognition that this opportunity is fleeting. The December question. By December 31st, when the practical observation window closes, we'll know whether humanity seized this opportunity or let it pass. We'll know whether the distributed network of amateur observers mobilized to collect comprehensive data. We'll know whether institutional resources were deployed appropriately. We'll know whether the mystery of 3i Atlas was investigated thoroughly or remained forever clouded by insufficient data. This isn't about believing or disbelieving exotic claims. This is about collecting evidence while evidence can still be collected. About answering questions while answers are still accessible.
About using the brief moment when an interstellar visitor is close enough to study before it disappears forever into the cosmic dark. The clock is running. The object is visible. The tools exist. What happens next depends on whether anyone actually looks. 6 weeks to see forever. Then silence. Then wonder about what we might have learned had we only bothered to observe while observation was possible. 4,000 years ago, on a clay tablet in ancient Mesopotamia, a scribe recorded an observation, a star that burns in the daytime traveling backward against the wheel of heaven. The cuneiform symbols pressed into wet clay and baked hard by the sun preserved the observation across millennia. We call such objects comets. They called them messages from gods. Were they so wrong? The ancient watchers knew something we sometimes forget. In our rush toward technological sophistication, the universe speaks.
It sends messages written in light and motion in the appearance and disappearance of celestial phenomena, in patterns that recur and anomalies that don't. The ancients lacked our instruments, but possessed something equally valuable: sustained attention across generations. Observations recorded and remembered patterns, recognized through centuries of watching, the precision of ancient astronomy. Modern archaeology and archaeoastronomy have revealed the extraordinary sophistication of ancient sky-watching traditions. This wasn't primitive superstition. This was systematic empirical observation maintained with remarkable dedication. The Babylonian astronomical diaries, spanning nearly 1,000 years from roughly 747 BCE to 61 BCE, recorded nightly observations of planetary positions, lunar phases, atmospheric phenomena, and unusual events. These weren't casual notations. They were detailed measurements using angular units that allowed calculation of celestial positions with surprising accuracy. When modern astronomers analyze these ancient records, they can verify observations eclipses occurred when the Babylonians said they did at the times and places recorded. Planetary positions match mathematical models of where those planets actually were in ancient skies. The records are reliable enough that astronomers use them to study subtle changes in Earth's rotation rate over millennia. The Babylonians could predict lunar eclipses using the Saros cycle, an 18-year, 11-day period, after which eclipses repeat with similar geometry. This understanding emerged from pattern recognition across centuries of observation. They didn't need to know why eclipses occurred, only that they followed predictable patterns. And knowing those patterns allowed prediction centuries in advance. Egyptian architectural astronomy.
The Great Pyramid at Giza, built around 2560 BCE, demonstrates precision that startles even modern engineers. Its four sides align to the cardinal directions with an accuracy of 3/60ths of a degree, about 3 arc minutes. This wasn't accidental. It required sophisticated astronomical observation using stellar transit methods or solar shadow techniques to determine true north. The 3 pyramids of Giza's necropolis mirror the configuration of Orion's belt. 3 stars in a diagonal line with relative spacing and brightness matching the pyramid positions and sizes. Orion held deep significance in Egyptian cosmology, associated with Osiris, god of the afterlife. The pyramids weren't just tombs, they were cosmological models, Earth mirroring heaven. The temple at Abu Simbel, built by Ramesses II around 1264 BCE, is oriented so that twice yearly on dates traditionally claimed as Ramesses's birthday and coronation day, sunlight penetrates the entire depth of the temple and illuminates statues of gods at the rear sanctuary. This required calculating solar position on specific calendar dates and orienting a structure accordingly. These aren't accidents or coincidences. They're deliberate applications of astronomical knowledge to monumental construction. The Egyptians understood solar and stellar motions well enough to design buildings that interact with celestial events. Mayan calendrical astronomy. The Maya developed multiple interlocking calendars of extraordinary precision. The Tzolk'in, a 260-day ritual calendar. The Hab, a 365-day solar calendar. The long count, which measured vast time periods. These calendars meshed in complex cycles, allowing the Maya to specify any date uniquely over periods exceeding 5,000 years. Their calculation of the solar year, 365.2420 days, differs from the modern measurement of 365.202 days by only 17 seconds annually. Without telescopes, without mechanical clocks, through observation alone sustained across generations. The Dresden Codex, one of only 4 surviving pre-Columbian Mayan books, contains astronomical tables, including what scholars interpret as Venus tables, predicting the planet's position across 584-day synodic periods. The precision is such that accumulated error amounts to only 2 hours over 500 years of prediction. How did they achieve this? Through dedicated observation maintained across centuries by astronomer priests who understood that the sky's patterns had practical and spiritual significance. They watched, recorded, calculated, refined, generation after generation, adding observations,
detecting patterns, encoding knowledge in calendars and architecture and text. Polynesian stellar navigation.
Perhaps most impressive because it required not just observation but applied synthesis were Polynesian navigation techniques. Without instruments, without written charts, Polynesian navigators crossed thousands of miles of open ocean, reaching islands they couldn't see from departure points using stellar positions. Ocean swells, bird behaviors, and accumulated knowledge passed through oral tradition. They memorized rising and setting positions of stars across the horizon, a natural compass encoded in stellar motion. They understood how different stars' paths across the sky indicated latitude. They recognized that certain ocean swells had characteristic periods and directions that persisted across hundreds of miles, providing orientation even when clouds obscured stars. This knowledge wasn't innate. It was developed through trial and error across generations, refined through experience, transmitted through apprenticeship.
It was empirical science practiced without writing it down, dependent entirely on accurate observation and precise transmission. The ancient interpretation of visitors. When unusual celestial phenomena appeared, comets, meteors, auroras, ancient cultures interpreted them within available frameworks. Without modern astronomy's explanatory power, they defaulted to the most sophisticated explanatory framework. They had divine agency. A comet wasn't a ball of ice and rock following orbital mechanics. It was a messenger, an omen, a sign from powers beyond human control. This wasn't ignorance, it was rational inference given available information. If you don't know about gravity, orbits, and physics, but you observe that celestial events sometimes precede earthly ones, inferring connection isn't stupid, it's pattern recognition. The Sumerian term dingir is sometimes translated as yagad, but literally means something like those of the bright sky.
Amur, their cosmology included beings from the heavens who brought knowledge and civilization. This could be purely mythological, or it could be how a pre-literate culture encoded observations of unusual celestial phenomena, interpreting them through narrative structures that preserved the observation even if the interpretation seems fantastic to modern sensibilities. The Dogon people of Mali have astronomical traditions that include surprisingly detailed knowledge of Sirius, including claims about a companion star Sirius B, which is indeed real, but wasn't confirmed by Western astronomy until the 19th century and wasn't photographed until the 20th. How the Dogons supposedly knew this before modern confirmation remains debated, with explanations ranging from ancient astronomical capability to contamination from modern sources. But the question illustrates how some ancient knowledge seems to exceed what we'd expect from their technological level. What ancients understood. Across cultures and continents, ancient sky watchers recognized something fundamental: the sky matters. Celestial events correlate with earthly seasons, with tides, with the passage of time. Watching the sky, carefully recording patterns, transmitting knowledge across generations, this wasn't superstition, this was survival. They also understood something else. Sometimes the sky sends anomalies. Sometimes events occur that don't fit patterns. Sometimes visitors arrive that demand explanation and interpretation. Their explanations invoked gods and omens because that's the explanatory framework their epistemology provided. We invoke physics and natural law because that's our framework. But the underlying recognition is identical. The universe contains regularities and exceptions, patterns and anomalies. Understanding requires attending to both. The perennial question. Every civilization that has watched the sky has asked, are we alone? What lies beyond our world? Do other realms, other worlds, other intelligences exist? The Sumerians carved their answer in cuneiform on clay tablets. The Egyptians built monuments aligned with the stars. The Maya developed calendars measuring time on cosmic scales. The The Polynesians sailed toward islands below horizons, trusting that patterns they'd learned would guide them true. Each culture sought connection with the cosmos through available means. Each recognized that the sky holds mysteries worth investigating, patterns worth understanding, questions worth asking. We continue that tradition when we observe three-eye atlas with modern telescopes, processing images with algorithms debating anomalies in online forums. We're asking the same questions the Babylonian astronomer priests asked when they watched the sky from ziggurats 4,000 years ago. Different methods, different vocabulary, same wonder. Same desire to understand what the universe is showing us. The bridge between ancient and modern. What if the ancients weren't primitive, just differently sophisticated? They lacked our instruments, but possessed our curiosity. They lacked our theories, but possessed empirical dedication. They lacked our mathematics, but possessed pattern recognition refined across centuries. When we observe three-eye atlas process images showing unexpected features, debate whether those features are real or artifact, struggle to reconcile observations with models, we're experiencing what ancient astronomers experienced when they encountered phenomena that didn't fit their frameworks. The discomfort of observation exceeding explanation, the tension between pattern recognition and interpretive uncertainty. They responded by watching more carefully, recording more thoroughly, discussing more seriously. Perhaps we should do the same. The ancient watchers knew when the sky sends a visitor, pay attention. Record carefully. Think seriously about what it might mean. Don't dismiss quickly what might be significant. The universe doesn't speak often in such direct terms. When it does listen, 4,000 years from now, what will future civilizations say about how we responded to Three-Eye Atlas? Will they praise our careful investigation and thorough data collection? Or will they wonder why, with all our instruments and understanding, we somehow missed an opportunity the ancients would have recognized immediately? A cosmic messenger arriving, demanding our attention, deserving our serious consideration. The observation window remains open. The message is still being delivered. The ancients would have mobilized every capable observer. Every priest astronomer would have been watching, recording, comparing notes. Are we less dedicated to understanding the cosmos than they were? Human beings are uncomfortable with uncertainty. We crave patterns, demand explanations, need closure. Our psychology evolved in an environment where uncertainty often meant danger. The rustle in the grass might be wind or might be predator. The tribe that assumed wind and was wrong didn't pass on their genes. We survived by finding patterns, by making predictions, by creating models of reality that allowed anticipation and control. But the universe is under no obligation to provide the comforts we crave. Reality doesn't care about human psychology. And sometimes, perhaps often, the most honest position isn't certainty but acknowledged uncertainty. The recognition that we don't know combined with the discipline to not pretend we do. The epistemological questions. What can we actually know? Not what can we hypothesize or theorize or speculate, but what can we know with confidence sufficient to build upon science? Attempts to answer this through methodological rigor. Observe carefully. Develop testable hypotheses. Gather evidence. Revise understanding based on what evidence reveals. But this process doesn't produce certainty. It produces provisional confidence. The confidence that our models approximate reality well enough for practical purposes, understanding that future observations might require model revision. Even our most successful theories, relativity, quantum mechanics, are acknowledged as probably incomplete, likely to be subsumed by more comprehensive frameworks as understanding advances. With Three-Eye Atlas, we have observations that don't comfortably fit existing models. We have images of uncertain provenance showing features that might be real or might be artifacts. We have institutional silence where we'd expect communication. We have legitimate questions without clear answers. What do we know? We know the object is interstellar in origin, that's definitive from orbital calculations. We know it has exhibited unusual color changes, brightness fluctuations, and water emission patterns that's documented by credible instruments. We know enhanced images circulating online claim to show structural features that's verifiable by examining the images themselves, though their correct interpretation remains disputed. What don't we know? We don't know whether the accumulated anomalies represent unusual but natural cometary behavior, catastrophic planetary fragment characteristics, or something more exotic. We don't know whether the structural features claimed in enhanced images are real or artifacts. We don't know why institutional sources have chosen silence over engagement. Most importantly, we don't know what additional observations might reveal if conducted thoroughly during the remaining observation window. Living with this uncertainty, neither dismissing observations nor overinterpreting them, neither embracing sensational claims, nor reflexively rejecting all unusual hypotheses, requires philosophical maturity, the ability to hold questions without forcing answers, to investigate without predetermined conclusions, to remain open without becoming credulous. Science at the edge. Throughout history, major scientific advances have come at the edge when observations didn't fit comfortable frameworks, when anomalies persisted despite attempts to explain them away, when paradigms proved inadequate to accommodate evidence. The Copernican revolution occurred because geocentric models, despite increasing complexity, couldn't comfortably explain planetary motion. The heliocentric model was resisted initially not because astronomers were stupid, but because it required abandoning a framework that seemed to work and that had philosophical and theological support. But evidence eventually became overwhelming. Darwin's theory of evolution was resisted by established biologists because it challenged frameworks about species fixity and divine creation. But evidence from fossils, from biogeography, from anatomy accumulated until resistance became untenable. The paradigm shifted because reality demanded it. Quantum mechanics emerged because classical physics couldn't explain atomic behavior, blackbody radiation, the photoelectric effect. Physicists didn't want to abandon classical framework. It worked wonderfully for macroscopic objects. But nature didn't care what physicists wanted. Evidence demanded new frameworks, however counterintuitive. Each paradigm shift faced resistance not from ignorance, but from expertise. Established scientists defending established frameworks. Resistance that eventually yielded when evidence became undeniable, but that delayed acceptance sometimes for decades. Could 3i Atlas represent a similar edge moment? Probably not. Most anomalies resolve through existing frameworks with minor modifications.
But the pattern is worth recognizing when observations persistently don't fit comfortable models. When multiple independent anomalies accumulate, when explanations require increasingly elaborate assumptions. Those are moments when paradigms sometimes shift. Not always. Usually further investigation shows the anomalies were measurement errors, artifacts, or phenomena explicable within existing understanding with minor refinements. But sometimes, occasionally, evidence reveals that reality is stranger than models accommodated, and frameworks must expand. The value of uncertainty. Mystery isn't the enemy of knowledge, it's the fuel. If we knew everything, curiosity would die. Questions drive investigation. Anomalies drive discovery. Uncertainty creates the space where new understanding emerges. 3i Atlas. Whether ultimately explicable through conventional cometary physics or indicative of something more unusual, has value in its mysteriousness. It's made astronomers look more carefully at interstellar objects. It's revealed gaps in our models of cometary behavior. It's demonstrated that our sample size of studied interstellar visitors is too small to make confident generalizations. Even if every anomaly resolves naturally, the investigation will have been worthwhile. Understanding why this object behaved unusually will refine models. Determining why enhanced images showed apparent features will improve image processing techniques. Explaining why institutional response was silence rather than communication will illuminate how scientific institutions handle uncertainty, and if some anomalies don't resolve comfortably within existing frameworks. Then we learn that the universe contains phenomena we hadn't anticipated, and understanding expands accordingly. Ancient wisdom traditions. While modern science emerged primarily from Western European traditions in recent centuries, other cultures developed sophisticated epistemologies, ways of knowing that handled uncertainty differently. Buddhist philosophy teaches don't know mind, the practice of holding questions without rushing to answers, recognizing that certainty often closes inquiry prematurely. The story of the Zen monk who responded to every question with, "I don't know," isn't about ignorance, it's about honesty. Not knowing is sometimes the most accurate position. Socrates famously claimed that his wisdom consisted in knowing that I know nothing. Not nihilistic skepticism, but epistemic humility. Recognition that confident claims about the nature of reality often exceed actual knowledge, that questioning is sometimes more valuable than answering. Taoist tradition embraces paradox, seemingly contradictory statements that point toward truths language struggles to capture.
The Tao that can be spoken is not the eternal Tao. Reality exceeds our conceptual frameworks. Models are maps, not territory, and maps always simplify. These philosophical traditions aren't anti-knowledge, they're pro-honest knowledge. They recognize that premature certainty can be more dangerous than acknowledged uncertainty, that questions are sometimes more valuable than wrong answers, that mystery has legitimate place in human relationship with reality. Perhaps modern science, in its appropriate insistence on evidence and testable hypotheses, sometimes loses this wisdom. Perhaps the discomfort with mystery drives premature closure, explains away anomalies, too quickly rejects hypotheses too reflexively when they threaten comfortable frameworks. Living in the question. Tonight, as you drift towards sleep, Three-Eye Atlas continues its journey overhead. It doesn't care whether we understand it. It doesn't care whether our models predict its behavior. It doesn't care whether institutional astronomers choose communication or silence. It simply is enigmatic, ambiguous, real. Perhaps that's the deepest lesson reality exists, independent of our explanations. The universe unfolds according to its own laws, not our preferences. Phenomena occur whether we understand them or not. And our relationship with that reality should be characterized not by desperate grasping for certainty, but by humble engagement with evidence. Honest acknowledgement of uncertainty and sustained commitment to investigation. We don't know what Three-Eye Atlas ultimately is. That's okay. That's honest. That's actually scientifically appropriate, acknowledging what we don't know while committing to learning what we can while opportunity exists. The mystery isn't failure. It's invitation. Invitation to observe more carefully, to question more seriously, to investigate more thoroughly, to remain open to whatever evidence reveals without forcing it to fit preconceptions. The ancient watchers understood this. When the sky sent something unusual, they didn't pretend to understand it immediately. They watched, they recorded, they wondered, they transmitted their observations to future generations who might understand better. We're those future generations. The ancient watchers would expect us to do what they did. Pay attention, record carefully, think seriously, not demand immediate answers, but commit to investigation. The observation window is closing. The mystery remains. That's not a problem to be solved in the next few weeks. It's a question to be investigated with whatever time and resources we can marshal. After Three-Eye Atlas departs, we'll have whatever data we collected. Whether that data is sufficient to resolve uncertainty depends on what we do now while observation is still possible. Whether future generations praise our investigation or wonder why we didn't do more depends on choices being made in these weeks.
The universe has sent a question written in ice and rock, traveling from stellar distances, briefly passing close enough to read. Are we reading carefully? Are we recording thoroughly? Are we investigating seriously, or are we too uncomfortable with uncertainty to engage honestly with mystery? Months from now, when Three-Eye Atlas has vanished into the cosmic dark, when analysis has been attempted, and debates have raged, and consensus has formed or failed to form, what will remain? Data will remain, observations captured during the brief passage, images verified, disputed, enhanced, raw, preserved in observatory archives and forum threads, spectroscopic measurements, brightness curves, calculated trajectories, the raw material of science waiting for interpretation. Questions will remain, whether the accumulated anomalies signified unusual but natural behavior, catastrophic fragment characteristics, or something more extraordinary.
Whether the enhanced images showed real structural features or processing artifacts. Whether institutional silence reflected appropriate caution or missed opportunity. But something else will remain too, the reminder that the universe still contains mysteries. That despite our sophisticated instruments and refined theories, we don't understand everything. That the cosmos can still surprise us, still challenge our frameworks, still present phenomena that don't fit comfortably into categories. That reminder has value beyond any specific answers about this particular object. Summary of confirmed facts. Let's be clear about what we actually know versus what remains speculative. Confirmed with high confidence Three-Eye Atlas III. Confirmed interstellar object in human observational history. Hyperbolic trajectory. Orbital calculations definitively establish extrasolar origin. Documented color changes, multiple observatories. Independently recorded neutral to red, to gray to blue transitions, brightness fluctuations. Published observations show variations not matching initial predictions, unusual water emission patterns. Swift Observatory detected hydroxyl signatures with concentrated distribution, images circulating online. Verifiable that images exist and are being discussed, though their correct interpretation remains disputed. Institutional silence, confirmed by absence of official statements or clarifications.
What remains uncertain? Authenticity and correct interpretation of enhanced images showing structure. Whether accumulated anomalies represent extreme natural variation or indicate something more fundamental. Explanation for the specific sequence of color changes observed, reason for the concentrated water emission pattern, cause of brightness variations that don't match simple rotation models. Why institutional sources have chosen non-engagement over clarification.
The ratio of confirmed to uncertain is important. The foundation is solid. This object genuinely has exhibited unusual characteristics, documented by credible instruments. The interpretation of what those characteristics mean remains open. That's honest science, confident about observations, appropriately uncertain about interpretation. The larger questions persist. Beyond the specifics of Three-Eye Atlas, this episode raises questions about how we investigate the unknown, how we handle observations that don't fit frameworks, how scientific communication works or fails in the digital age. Are we alone in the universe? Remains humanity's most profound question. Not because we need a definitive answer, perhaps we never get one, but because asking it shapes how we understand our place in reality. If we're alone, the universe is radically different than if we're not. Our philosophical frameworks, our sense of meaning, our understanding of life's place in cosmic history all depend on this question's answer. Three-Eye Atlas probably doesn't answer it. Probably it's a natural object, however unusual. But probably isn't certainly, and the possibility, however remote, that an interstellar visitor might carry information about other worlds, other processes, perhaps even other intelligences, demands serious consideration. Has intelligence elsewhere reached the stars, connects to the first question but adds technological dimension. Life might exist elsewhere but remain planet-bound. Technological capability sufficient for interstellar travel or probes represents a threshold that, if crossed by any civilization, changes the question from, "Is life elsewhere?" to, "Could evidence of that life reach us?" Does our solar system occasionally receive visitors, natural or otherwise, is answerable through observation but requires sustained attention. If interstellar objects pass through regularly, and statistical models suggest they do, then systematic survey and careful characterization should be priorities. Each visitor carries information about conditions beyond our solar system. Each deserves thorough investigation. What is science's responsibility when data is ambiguous gets at methodology and communication. When observations don't fit comfortably into existing frameworks, when multiple interpretations remain viable, when uncertainty persists. What's the appropriate response? Silence until consensus emerges. Open discussion of competing hypotheses. Acknowledgement of uncertainty while investigation continues. This isn't abstract philosophy. It's practical epistemology with real consequences. How institutions handle ambiguous data affects what questions get investigated, what observations get prioritized, what resources get allocated, what knowledge gets gained or missed. Ancient echo modern question. 4,000 years ago, humans watched comets and asked, "What are these messengers?" The vocabulary was mythological divine omens, celestial signs, messages from gods. But the underlying question was epistemological. What does this phenomenon mean? What information does it carry? How should we interpret what we're seeing? Tonight we watch 3i Atlas and ask structurally identical questions. The vocabulary has changed: spectral analysis, orbital mechanics, compositional modeling. The instruments have improved charge-coupled devices, computerized tracking image processing algorithms, but the wonder remains identical. Something has arrived from beyond our familiar realm, something that didn't originate in our solar system, that traveled distances almost beyond comprehension, that briefly passes close enough to observe. What is it? What does it tell us? What does its arrival mean? The questions haven't changed in 4 millennia. The tools for investigating them have. But the fundamental human impulse to observe, to question, to seek meaning in what the universe shows us, that remains constant across cultures and centuries. Personal reflection. Whether 3i Atlas is an unusual comet, a planetary fragment, or something more extraordinary matters scientifically. The specific answer will inform our understanding of interstellar objects of cometary diversity, potentially of our place in the universe. But regardless of the specific answer, 3i Atlas has given us something precious. A reminder that the universe still contains mysteries. In a world of instant answers and algorithmic certainty, where search engines deliver information in milliseconds and artificial intelligence claims to know everything, genuine mystery is rare. Actual uncertainty, the honest acknowledgement that we don't know and might not find out, is uncomfortable enough that we often avoid it. 3i Atlas forces that discomfort. We don't know what it is not completely. We might never know. It will depart before investigation is complete, carrying unsolved mysteries into interstellar space, leaving us with incomplete data and persistent questions. That's frustrating to our desire for closure. It's appropriate to reality's actual nature. The universe doesn't exist to satisfy human curiosity. It doesn't provide neat answers to every question. Sometimes, perhaps often, we encounter phenomena we can't fully explain with available data, and that's okay. That's real. That's honest. The gift of uncertainty is the reminder that we don't know everything, that understanding remains incomplete, that the cosmos still has secrets. That wonder is not childish, but essential. The gift of perspective. Every time humans encounter something from beyond our immediate environment, whether a rock from space, a signal from the depths, or an interstellar visitor, we gain perspective on our place in a larger context. Earth is one world among countless trillions. The Sun is one star among hundreds of billions in our galaxy alone. Our galaxy is one among hundreds of billions in the observable universe, and the observable universe is likely a tiny fraction of reality's full extent. In that context, the arrival of an object from another stellar system isn't just scientifically interesting, it's philosophically profound. It's a physical connection to realms we'll never reach, to processes we didn't witness, to a universe vastly larger than our direct experience. Ancient peoples knew this instinctively. When they watched the sky, they felt connected to something greater than individual human life, than tribe, than world. The cosmos dwarfed them, humbled them, inspired them. We have the same opportunity with 3i Atlas, to feel connected to cosmic processes, to recognize our smallness in context without diminishing our significance, to experience wonder not as entertainment but as appropriate response to reality's genuine strangeness.
That feeling that wonder is worth preserving, worth cultivating, worth protecting from the cynicism that dismisses mystery as naive, from the know-it-all confidence that pretends understanding is complete, from the institutional caution that prefers silence to honest acknowledgement of uncertainty. The observation window is closing. By year's end, 3i Atlas will be too distant for meaningful amateur study. It will become an entry in astronomical catalogs, a designation, a set of coordinates, a collection of disputed data points. Professional observatories might continue tracking it, but that data may not be publicly available for months or years, locked behind peer review processes and institutional publication schedules. But for 6 weeks in late 2025, it was more than catalog entry. It was a question mark hanging in the pre-dawn sky, a cosmic Rorschach test revealing what we're willing to consider, what we're afraid to entertain, what we hope for in the darkness between stars.
The ancient Egyptians believed the sky was a great stone vault, punctured with holes through which divine light shone what we call stars. They weren't entirely wrong. The vault exists, though it's distance rather than stone. The holes exist, though they're distant suns rather than divine portals. The light shining through is real, carrying information about realms we can barely imagine. But perhaps the Egyptians were right about something deeper. The sky still speaks, still sends messages, still invites interpretation. The vocabulary has changed from mythology to physics, but the essential relationship, humans looking up, seeking meaning, trying to understand what the universe is showing us, remains constant. 3i Atlas came from somewhere we cannot imagine, traveled distances that break human comprehension, and so briefly passed close enough for us to see, to photograph, to analyze, to wonder about. In 6 weeks, it will be gone. The data will remain. The debates will continue. The mystery will persist or resolve according to evidence we haven't yet fully collected or analyzed. But this moment when an object from the stars is visible overhead, when you could go outside and point toward Leo and know that somewhere in that region of sky, something from beyond our solar system is passing through. This moment is rare, precious, perhaps sacred. Our ancestors would have made offerings, built temples, created myths to encode their observations for generations to come. We create forums, process images, debate hypotheses. We apply scientific method rather than mythological interpretation. Different expressions, same impulse. The universe has sent a messenger. We're still learning how to read the message. And so, as you drift towards sleep tonight, consider this. If 3i Atlas carries within it the answer to humanity's oldest question, are we alone? Would we recognize that answer if we saw it, or have we already seen it, captured it in our photographs, analyzed it with our instruments, discussed it in our forums, and simply not known what we were looking at? The stars wait patiently. They've been waiting for billions of years, since before Earth existed, since before the sun ignited fusion in its core, since before the molecular cloud from which our solar system formed began collapsing. They can wait a little longer for us to learn their language, for us to develop the wisdom to recognize when the universe is speaking directly to us, for us to overcome our fear of uncomfortable answers enough to ask uncomfortable questions honestly. Sleep well, and when you wake, if the sky is clear and the hour is right, look east before dawn. Look toward Leo.
And know that something is out there, something that traveled from distances almost beyond imagination, something that raises questions we haven't fully answered. The observation window remains open, not forever, just a few more weeks. The sky is still speaking. We're still learning to listen. And perhaps, just perhaps in the silence between our questions and the universe's answers, in the space between what we know and what we wonder, in the mystery that remains after investigation concludes, perhaps that's where the most important truths reside. The truths that can't be captured in equations or confined to categories. The truths that can only be experienced through direct engagement with wonder. Three-Eye Atlas is more than comet, more than data, more than mystery to be solved. It's a reminder that we live in a universe stranger and more magnificent than our models can fully capture. A universe that still sends visitors from the depths.
A universe that still speaks to those willing to listen. The message continues. The interpretation remains incomplete. The wonder endures. Look up. The sky has not finished surprising us.